vectors now switch gears a little bit. So now we have a magnitude and a direction. Before functions, they could just go on forever. And if we integrate, we usually go over a specific region for our definite integral, or we can go on forever to infinity as well. We can go over the entire xy plane, which is fine, or we can restrict the domain, or but normally when we have a line goes on forever and it never ends. A vector, on the other hand, will end. It will have a beginning point and a terminal point, a start and an end. So if we draw, like let's say we have a two-dimensional vector, we can start at the origin and end at some particular point. We can call that vector r. And this is going to have an angle to the horizontal. Vectors start at A, so A to B, and sometimes it's written like this or like this. Actually, I don't know about that one, but I've seen them for sure written like these. A would be the x component, y would be the y component. So we can also kind of say, oh, well, we go this far on the x-axis, and then we go this far up on the y-axis, and this is our vector again. It's like an ordered pair, except instead of just having some random point, now we draw an arrow to that point. Vectors can be added, so if we have a comma b plus c comma d, you can say a plus c comma b plus d. Geometrically, we can also say if this and this are vectors, we can, that's not a vector, but this line is in the middle and it's not a vector. We could say, we could do the tip to tail. We could say, okay, well, we can do that and then that, and that's our vector. Subtracting is the same thing, except, now we're going in the opposite direction, so it'd be like going down. If we're adding the opposite of this vector, let's say a and b, and this is a, and we add the negative of b, we're going to go down instead and end up like somewhere right there. That's like the tip to tail method. But we can also just add the components all together. Vectors, there are little different rules for vectors. First, vectors are usually 3D, although there are higher dimension. Typically, I think 4D shows up for space-time, for like general relativity, but usually 3D works. So we could say A, B, C. And the same rules apply: A plus B, B plus E, A plus D, B plus E, C plus F, so on and so on. We have the dot product. The dot product basically A dot B is equal to, let's say this is A and this is B. A times D plus B times E plus C times F. And this is useful for not just finding the angle between the vectors, but we have this neat little theorem that says that A dot B is equal to the magnitude of A times the magnitude of B times cosine of theta. Oops, that line went through a little bit too far. Or rearranging cosine theta is equal to A dot B over the magnitudes of the vectors. And the magnitude, let's say the magnitude of A, that's going to be the square root of A squared plus B squared plus C squared. Similarly, for B, that's going to be the square root of D squared plus E squared plus F squared. The square root of the square of each component, basically. So we have this condition, like the cosine of A dot B over the magnitudes. So if they're orthogonal to each other or perpendicular, that means that they have a 90 degrees in between each other. And if A dot B is equal to 0, then that means that they are perpendicular or orthogonal. For example, if we have 1, 2, 3, and we have 4, negative 2, 0, A dot B then is 1 times 4 plus 2 times negative 2 plus 3 times 0, which is 4 minus 4, which is 0. So these two vectors are orthogonal. There's also the cross product. The cross product is a little trickier. This will produce another vector that is orthogonal to both. So if we say vector C is A cross B, this is how you say it, A cross B. Then this is just X hat, Y hat, Z hat. Although mathematicians will usually use I, J, and K, I like to use X, Y, and Z. And these will have the components of A, B, and A and B. So A1, A2, A3, and B1, B2, B3. And then you just take the determinant of this, which I will explain in another course, but the determinant of a 3x3 matrix is essentially do the cross-out method. So it would be like, this would be for our X component. So A2, A3, B2, B3 minus the Y unit. And now the cross-out method. So A1, A3, B1, B3. And now we're going to add the Z unit. And the cross-out method would be A1, A2, B1, B2. And now when we take the determinant of these 2x2 matrices, it would be just the cross term. So X unit times A2 B3 minus A3 B2, and then minus Y unit times A1 B3 minus A3 B1, plus z unit times a1 b2 minus a2 b1. And that's the cross product. So if we use that same two vectors before, 1, 2, 3, and 4, negative 2, 0, we end up with these matrices, and now we take the determinant of each and we find that x unit. We find that the x component is 6, the y component is negative 12, which is 12, and then our z component is negative 10, so our vector is just 6, 12, negative 10. I suppose I should write those units differently. When it has a hat like this, that means it's the unit vector in a certain direction. These hats are, x hat is a unit vector in the x direction, the y direction, and the z direction. It's the length of one is the unit vector. And that's about it for this basic vector video. So we started with our components. We said we can add vectors, and then we said we can multiply them, and multiplying them gives the angle in between the vectors. Vectors can be perpendicular to each other if their dot product is equal to 0, and then we can make another vector which is perpendicular to both of them, and this goes through a 3x3 matrix, and then we break that down and get a completely separate vector. Anyway, thanks for watching.